Hello, let's consider this 10th problem. It reads electric field lines of a portion of an electric field that is symmetrical with respect to rotation about y-axis is shown in this figure. A charged particle stays in equilibrium at point 0, 10, that is this location. If modulus of this charge is changed gradually till it shifts another equilibrium position at origin, we need to estimate fractional change that has to be brought into this charge modulus. So how it is going to be at equilibrium and what are the situation? Let me explain that thing first. So these are part of field lines, and it has been shown only for x-axis, positive x-axis with y. Now if we look from the top, maybe then you'll find is going to be symmetrical about y-axis. So these field lines are symmetrical from the y-axis. That means they will be, if you consider this kind of circle in this xz plane, they will be moving in this way, in all the way symmetrical. So these are the field lines. Next, how it is going to be at equilibrium at this location or at this point, then you'll find at this point electric field is going to be there. That electric field is going to apply a force of electrostatic, and there's going to be non-contact force due to gravity. Gravity is acting downwards, so you'll find gravitational force and electrostatic force, they are balancing each other. So basically we need to go with Q is equal to mg. Now when we are at the point initial, then let's say Q1 charge was there and field at that location is E1, that will be balancing mg. Now when we are changing this charge, accordingly this E will change so that the product remains mg. At location 0, 0, let's say charge becomes Q2, field is E2, and is going to be equal to mg. Basically from these two relations we can say Q1 E1 must be equal to Q2 E2. Now since Q2 has reduced, that means E2 must have gone up, and you can think of here field line density is more as compared to there. That means field line electric field strength has gone up as we moved from 10 to 0 along the y-axis. So basically from here we are getting Q2 upon Q1 is equal to E1 upon E2. That means we need to find the ratio of electric field at this location initial as well as at this final location. Now how to find the electric field strength ratio? That's going to be important point. And if we are able to find this, we can find out the fraction, this change in ratio of the charges, and then we can find the fractional change. Now this electric field strength is directly proportional to the field line density. That means number of field lines per unit area. Let's consider one area in 3 dimensions, and let's take a radius equal to 5, because this up to 5 we can take any radius, or we can take even a smaller radius. So we are considering 5 radius, and we are thinking about a circle. There is a one circle of radius 5 at origin, which is lying in the z-x plane. Consider the same amount of area lying in this this xz plane, but having center at 0, 10. Now from these areas, how many field lines are passing? That will give us the idea about or values about electric field strength. So we will say the number of field lines passing through this area is going to be give E1. The number of field lines passing through this area is going to give number E2. So we can, if we can find out how many field lines are passing through the first and the second, so ratio is going to be E1 by E2. Now we need to find the number of field lines passing through these areas. Now if you look this 2-dimensional picture, then up to 5 centimeter we can measure in this linear fashion how many field lines are there. So if we are in the top 10 points, then you'll find up to 5 you will go from here to there. How many field lines in linear situation we are getting? So this field line must be crossing, this field line must be crossing. Now this is radial, right? And if we convert into area, so it's like we know the radius, we need to know the area. So how the radius and area are related to each other? So we say area is pi r square. So we can say the number of field lines will also be in the similar form as we calculate the area out of radius. So we can say here the field lines will be square of 2. So we will say E1 by E2 is going to be 2 square divided by the area. Area is pi r square, r is 5 centimeters, so that's going to be the same for the 2. So this will become the field line density for initial location. Now we need to identify the field line density for the later location. So for this circle, again in this circle, these lines we need to count. You can count this 1, 2, 3, 4, 5, 6. So these 6 lines are lying along the line. Now if we convert, if we try to find these total number of field lines through the area, so we can extrapolate it, and we will find this area, number of field lines through the area is going to be related in a very similar fashion as this radius is related with this area. So we will say it's going to be like 6 square divided by the area, which is geometrical area pi r square. Since we have taken the same area for the two, so they will get cancelled out. So basically we are going to get 2 square by 6 square, that is 1 by 9. So we got to know the field strength ratio is 1:9 at these two locations. Once we are able to do this, then it's done. From this equation we can find Q2 upon Q1 is come out to be 1 by 9. You can subtract these from 1. So 1 minus Q2 by Q1 is equal to 1 minus 1 by 9. And this left hand side will become Q1 minus Q2, that is change in the charge divided by initial charge. Basically it's trying to say fractional change in the charge. That is what we are supposed to estimate. So fractional change in the charge is going to be 8 by 9. And we can see option D is 8 by 9, which is the correct response. Thank you.